Hey everyone, welcome back to the channel Code with AKJ. So this is day 15 of solving LeetCode 75 and today we are solving an exciting problem from sliding window concept, that is maximum number of vowels in a substring of given length. So the question says here, given a string s and an integer k, return the maximum number of vowel letters in a string of s with length k. So if you are preparing for coding interviews or sharpening your algorithm skills, this one's for you. So stick around as we explore both the brute force and the optimal sliding window approach, and I'll break it all down step by step. So let's look at some examples. Given example 1, input S, which is A, B, C, I, D, E, F, and K value is 3. So in this given example string S, the substring I has 3 vowels. So we'll return 3 here, which is the maximum number of vowels in this given substring. And coming to the second example, A, E, I, O, U, and substring length should be 2. And here the substring length 2 has 2 vowels, which is A, E, or E, I, or I, O, or O, U. So any of these substring has length 2 and has 2 number of vowels. And coming to the example 3, string S LeetCode with length K value 3. We have 3 substrings having 2 vowels, which is the maximum number of vowels in this given length 2 substring. So which is LEE, EET, and ODE. So let's start with our simplest approach, that is brute force approach. So the steps here would be to iterate through all the substrings of this given string S, which is of length K, and for each substring we'll count the number of vowels and we'll keep track of the maximum count. So this would be our simplest approach, which is brute force approach. So let's try to quickly code this approach, and later on we'll move on to our optimal approach, where we'll solve this given problem using sliding window algorithm. So we'll take a variable max count, which would be initially 0. We'll loop through our string S, and since we are grabbing the substrings of length k, we'll move until or unless the I becomes less than or equal to s dot size minus k. And next we'll keep a count of vowels for a given substring k. We'll use another for loop which starts from I till I plus k. And using this for loop, we'll check for each substring s of length k whether this particular character, current character, is a vowel or not. We'll use an external function isVowel, and if it returns true, we'll increment our count value. And after finishing our for loop, we'll update our max count value using max of max count, and we'll compare it with the current count value. And finally, we'll find our max count value, which is the maximum number of vowels in a substring of given length k. We'll return this max count at the final step. So let's quickly complete this isVowel function. IsVowel function takes character C as a parameter, so we'll check for every vowel whether this current character is with any of this vowel or not, which is A, E, I, O, U. So let's try to run this code. So let's submit. As you can see, this approach gives us time limit exceeded. So let me just quickly explain this given approach and this code. So we use 2 loops here. The outer loop generates the starting indices of all the substring of length k, and the inner loop counts vowels in each substring. So here the time complexity would be O of n cross k, where n is the length of the string s, and space complexity here would be O of 1. So since this approach gives us time limit exceeded, so it becomes slow for larger inputs, so as it examines every substring explicitly. So we can do better. So let's move on to our optimal solution, which is using sliding window approach, which reduces the complexity significantly. So let's solve this question using our sliding window approach. So in our optimal approach, instead of recomputing the vowel count for every substring, we can maintain a running count of vowels using the sliding window. So steps here would be to initialize a variable count, which would be initially 0. It generally stores the number of vowels in this current window. So we'll maintain a current window of size k. we'll use a single loop to slide this window through the string, and we'll add the character entering into the window to the count if it is a vowel, and we'll subtract the character leaving the window from the count if it is a vowel. So after finishing these two steps, we'll update the maximum vowel count. So we'll also take a variable maximum count. So this would be our steps in our optimal approach. So let's quickly recap our steps. So we'll take a variable count which will store the number of vowels in the current window, and we'll use a single loop to slide our window through the string. We'll add the character entering into the window and to the count if it is a vowel, and we'll subtract the character leaving the window to the count if it is a vowel. And finally, after adding and subtracting the characters to this current window, we'll update our maximum count. So let's quickly code this optimal approach where we have used sliding window approach, and let's quickly dry run. So here's the code for our optimal approach where we have used sliding window technique. Here I've taken two variables, count and max count. I've looped through this string s, and I'm maintaining a window of size k. This step would add vowel to our current string while incrementing our count variable, and this would be our removing character condition where if it is exceeding from our current window condition and it is also a vowel, so we'll deduct that value from our count variable. And finally, we reached the current window of size k. We'll update our max count variable with the current count variable. And finally, we are returning max count variable, which stores maximum number of vowels in a substring of given length k. So let's quickly run this code. So let's submit. As you can see, it got successful submission. So here the sliding window ensures that we only adjust the vowel count by adding the new character and removing the old one. So here the time complexity would be O of n because we process each character exactly once, and it's efficient and scales well for large strings as well. So let's quickly dry run our optimal approach using this given example, string s and k value 3. So initially we'll keep our count variable 0 and max count variable 0. So sliding window starts with first k characters. So iteration 0 starts with current character a. So here the current character a is a vowel, so we'll update count value to 1. And since I is less than k minus 1, we don't update our max count variable. So next iteration 1, our current character is b, which is not a vowel, so count remains 1. And since I is less than k minus 1, we don't update our max count. Next we move to iteration 2, where current character is c, which is not a vowel, so count remains 1. And since I is greater than or equal to k minus 1, which is we have reached a current window size of k length, we'll update our max count variable with our current variable count. So we'll update our max count variable from 0 to 1. So next iteration 3, our current character is I, which is a vowel, so we'll update our count variable from 1 to 2. And character leaving this window would be a, which is also a vowel, so we'll decrement our current count from 2 to 1, and we'll update our max count, which is max of 1 comma 1 is 1, so it remains 1 itself. So next iteration, our current character is I, which is a vowel, so our count variable becomes from 1 to 2, and the leaving character here would be b, which is not a vowel, so we'll update our max count from 1 to 2. So next window here would be c, I, and I. So the current character here is I, which is a vowel, so we'll increment our count variable from 2 to 3, and the leaving character here would be c, which is not a vowel, so the count remains 3, and we'll update our max count from 2 to 3. So for next iteration, the current character is d, which is not a vowel, so the count remains same, and the leaving character is a vowel, so we'll decrement our count variable from 3 to 2, and we'll update our max count, which remains 3 as well. So for the next iteration, the current character is E, which is a vowel, so we'll increment our count from 2 to 3. And the leaving character here is I, which is a vowel, so we'll decrement our count variable from 3 to 2, and we'll update our max count variable, which is 3 itself. And for the final iteration, which is F, is not a vowel, so the count remains 2 itself, and the leaving character here is I, which is a vowel, so we'll decrement our count value from 2 to 1, and our max count variable would remain same. So since we reach at the end of the string, we'll stop our iteration, and from this given example string S, our max count variable, which is the number of vowels for a given string of length k, would be 3, and the substring would be I, and I. So the time complexity here would be O of n, and space complexity here would be O of 1. So let's quickly analyze the time complexity and space complexity of both the approaches we have discussed so far. So for the brute force approach, the time complexity was O of n cross k, and space complexity was O of 1. Whereas coming to our optimal approach, where we have used sliding window technique, the time complexity was O of n and space complexity was O of 1. So while the brute force approach is simple but slow for larger inputs, whereas the optimal approach is fast and efficient for both inputs. And that's it guys, we have solved the problem using both brute force and sliding window approaches. So if you found this video helpful, don't forget to like, share and subscribe. Drop a comment below if you like me to cover more problems like this. So keep coding, and I'll see you in the next one. Thank you.